G'day and welcome back to Mathematics for a brand new term of HSC prep and mathematics and lots of good stuff. Today I'm diving back into the Extension 1 playlist looking at some further trigonometric equations. Going to do a couple of lessons on this. Next one's going to be uploaded in a couple of weeks, so subscribe if you want to see it. Before we dive into today's lesson, let's just do a quick revision of some important concepts that we're going to need from the Year 11 course, starting off with this flashback question. We have, if cos theta is equal to -3/4 and theta is between 0 and pi, find the exact value of tan 2 theta. Okay, now typically any question where you are given one of the trigonometric fractions and you're trying to find one of the other fractions and you want to find it exactly rather than doing a bit of a dodge job with your calculator, best thing to do is to start off by drawing yourself a little triangle. We're going to draw a right angle triangle. I'm going to put a theta in either of the corners. Mine's going to go up here. Okay, now if theta is in the top corner of this triangle and we want cos theta to be equal to 3/4, well, this means that adjacent side needs to be 3 and hypotenuse needs to be 4. We're not going to worry about the negative for now. We're just going to focus on the numbers and then work towards getting something we can work towards for tan theta. Okay, so if I want to use this triangle to figure out some tan theta or some sine theta, I would need to find the other side over here, which is the opposite side. Luckily, when you have 2 of the 3 sides in a right angle triangle, you can apply a bit of year 8 Pythagoras and just do 4 squared, take away 3 squared, which is going to be 16 minus 9, which is 7. So this side is going to be the square root of 7. Okay, now cool. What we need to figure out now is which quadrant we are in. So because we said that theta is between 0 and pi, this means we're in either quadrant 1 or 2. But because it says that cos theta is giving us a negative value, that only happens in quadrant 2, okay? In quadrant 1, all sine, cos, and tan are positive. So for cos theta to be negative, it tells us that theta is going to be in quadrant 2. Now that's important because in quadrant 2, sine theta is positive, but tan and cos are both negative. Okay, so to figure out tan 2 theta, we're going to first of all note down that tan theta now is opposite over adjacent, so root 7 over 3. But like I said, because we are in quadrant 2, as we figured out, we're going to have a negative value for tan theta. Now, to work towards tan 2 theta, we need to use this identity from our reference sheet, which is the sum angle for tan. We're going to take this and we're going to replace A and B to both be theta, which is going to turn the left-hand side into tan 2 theta. So over here, we'll have tan theta plus tan theta over 1 minus tan theta squared. So we're going to have tan 2 theta is equal to 2 tan theta over 1 minus tan squared theta. This second line in red is something that I strongly encourage my Extension 1 students to memorize. So you don't have to jump through this first hoop every time, and it's just going to make you a more efficient and quick mathematician. Okay, so to figure out tan 2 theta, all we need to sub in is tan theta, which we've figured out up here in blue. We're going to substitute this into the right-hand side of the equation. So we're going to have 2 times negative root 7 on 3 for the top of our fraction. And on the bottom, we have 1 take away negative root 7 over 3 being squared. This is our answer. Now we just need to tidy it up and try and make it look as nice as possible to get full marks. So we'll make some space and we'll do that. On the bottom, when we square this, we're going to have positive 7 over 3 squared, which is 9. So we have 1 minus 7 over 9, and that's why the bottom turns into 2 over 9. Now we can just chuck this big fraction into a calculator, but that'd be boring. Let's just multiply top and bottom by 9. So the bottom is now going to turn into 2 because the 9's gone away. When I times the top by 9, 2/3 of 9 is 6. So I end up with negative 6 root 7 over 2. And then I can simplify this by just doing 6 divided by 2 is 3. And we get our final answer of negative root 3 root 7. So this is the crux of what we're doing today. We are relying on our knowledge of trigonometric identities, which is hopefully something you explored a little bit in the Year 11 prelim course. We're going to apply these skills to solve equations, which is very challenging. I'm going to do a bunch of examples, go as slow as possible, and hopefully you get some value out of this. So today's lesson is on trig identities and equations in the Extension 1 course. Let's dive right into it with our first equation. Okay, example 1, we are solving for x in the set of 0 to 2 pi. So this means in one lap of the circle from 0 to 360. We have sine of x plus pi on 6 minus sine of x minus pi on 6 is equal to 1. Now, the moral of the story with this first example is that please be aware that on the Extension 1 and Extension 2 and Advanced reference sheet, there is a lot of information. There is a lot of information regarding trigonometry, and a lot of it's going to be very useful. So when you are looking at some trigonometry, especially in an equation, and you're really not sure how to handle it, first thing I would recommend you do is grab the reference sheet and look for something that's going to be useful. In this question, you might notice this. Okay, this thing in red is on the reference sheet, and what we're seeing is we have sine of two angles plussing minus sine of the same angle's minusing, and the left-hand side is the simplified version of the right-hand side. We can simplify this by simply writing it as 2 times cos of the first angle times sine of the second angle. So in the context of our equation, we have the right-hand side, we have sine minus sine, and our a's and b's inside the brackets are x and pi on 6. So we can apply that and say, cool, if I use this information in red from the reference sheet, I can simplify this by looking at the left-hand side and just do 2 times cos times the first angle, which is x, and then multiply that by sine of the second angle, which is pi on 6. And so the right-hand side is the significantly simplified version of the left-hand side, and it's going to make our life easier. We're going to take our equation in black from the first side, and we're going to make this change in green. We're going to change the sine minuses into a 2 cos x sine pi on 6. So now that's the left-hand side equal to 1. Luckily, sine pi on 6 is just a number. This is sine of 30 degrees, which is just equal to a half. So we have 2 times cos x times a half is equal to 1. That's really convenient because now we have 2 multiplying with a half, and so that just gives us a 1. So we end up with just cos x equal to 1. Okay, now this is our equation we are trying to solve. Whenever you're trying to solve sine or cos or tan equal to 0 or 1, the best thing you want to do is think about what the graph of cos x looks like. Okay, if I was a good maths teacher, I would have put a picture in this slide, but I think I forgot. But hopefully you can close your eyes and visualize cos x. It's a curve, it's a wave that starts at 1 when x is equal to 0, and then it loops back around after 360 degrees. Okay, so I'm tracing out with my mouse now. The first value where cos is equal to 1 is at the start, 0, and the second value is at the end, 2 pi, starting at 1 and then finishing at 1. So yeah, a really highly recommended skill for advanced and especially extension students is you really need to have your graphs of sine, cos, and tan memorized because they're super useful for a lot of parts of the course, not just solving equations. So yeah, going from here to here by picturing the graphs is a really, really useful skill that I recommend all students work on if they aren't already there. But there's our answer, 0 to 2 pi in our range. Okay, moving on to the next one, example 2. We have a bit of a mess here. We've got some Greek alphabet soup going everywhere. We've got, given that cos of theta minus phi, another Greek letter, is 3/5, and tan theta tan phi is equal to 2, find the value of cos theta plus phi. Okay, let's think about cos theta plus phi. We have an identity we can use on our reference sheet that we can use to expand cos of an angle plusing with another angle. It tells us that cos of a plus b is equal to cos a cos b minus sine a sine b. So I'm using that information from the reference sheet, but I'm changing a to be theta and I'm changing b to be phi. So now looking at what we're trying to figure out, we are trying to figure out cos theta cos phi and sine theta sine phi. Let's go back to the information from the question and see if we can build towards these parts in blue. The first thing we have is that cos of theta minus phi is equal to 3/5. So we'll once again use an identity from the reference sheet, which is a statement I'm going to say a lot today, and we are going to expand out cos of theta minus phi. When you do that, it looks like this. It's the same thing as before, but instead of a minus in the middle, it swaps, so it's going to be a plus. So cos of a minus b is cos a cos b plus sine a sine b. But again, once again, the a is theta and the b is phi. Okay, so we have cos theta plus, we have the coses and the sines plussing together, getting us 3/5. Not much more we can do with that. Let's think about tan theta tan phi equal to 2. So far, everything we're working with in the question is involving coses and sines, so it's probably a good idea to turn our tan equation into something involving coses and sines. Luckily for this one, we can use the fact that tan is equal to sine over cos. So that means that tan theta tan phi is equal to sine theta sine phi over cos theta cos phi. So again, we've translated the tans into sines and coses because that's what the rest of the question is doing, and we need to make stuff match so we can use some stuff together. All right, let's multiply the cos theta cos phi across the right hand side. So we get sine theta sine phi equals 2 cos theta cos phi. Now we're going to ready to combine the green and red equations together to try and work towards the blue equation, which we can do because now we can take the red equation, and wherever we see a sine theta sine phi, over here in green it says that sine theta sine phi is equal to 2 cos theta cos phi. So let's substitute that into here and change that to a 2. Okay, cool. I'm going to need some space now, so let's just move some important stuff out of the way. So the important stuff is still there, but that was the last line from the last slide. Okay, now this is good because we have cos theta cos phi and 2 cos theta cos phi, so we can just group these together. This is like x plus 2x. We can just write that as 3 lots of cos theta cos phi. Now we can divide both sides by 3 and we get cos theta cos phi is equal to 1/5. And now we're halfway towards our answer in blue. We have cos theta cos phi. All we need now is sine theta sine phi. So to figure that out, we'll use the other half of the simultaneous equations we were working with earlier. We'll go over here to the green, and where we see a cos theta cos phi, we can now replace that with its value that we know is equal to 1/5. So over here we get sine theta sine phi is equal to 2 times 1/5, which is 2/5. And now we have both pieces that we need to get a value of our expression in blue here. We can substitute them in and say this one is going to be 1/5 minus this one, which is going to be 2/5. So we get 1/5 minus 2/5, which is negative 1/5 for our final answer. So there you go. Lots of identities getting involved here. Like I said, when you're lost, look to the reference sheet and there's heaps of stuff there that is designed to help you exactly with questions like this. Okay, on to the next example. Stepping up again. We have solving for x in the region of minus pi to pi. Our equation is sine x cos x is equal to 1 over 2 root 2. Okay, let's think about this. So personally, as a maths teacher and someone who's done a lot of extension maths, whenever I see sine x and cos x multiplying together, here's where my brain goes. I think, hey, 2 times sine x cos x is equal to sine 2x. This is the sine double angle identity, and is once again something that I strongly recommend you memorize because it's not, tragically, on the reference sheet. If you forget this, you can get there pretty quickly by using the information in black here, which is on the reference sheet. This is our sum of angles for sine. You can start here and you can change a and b to both be x, and on the left hand side you get sine 2x, and on the right hand side you get sine x cos x plus cos x sine x, which is just 2 sine x cos x because they're the same thing. But that's the long scenic route. I really recommend memorizing the thing in green because it's going to make your life a lot easier. Trust me on that one. Okay, to apply this to our equation, we need to have 1 sine x cos x. We're just going to cut these in half and say, well, that means that sine x cos x times 1 is going to be a half of sine 2x. So the thing here in red is just the equation in green, but both sides divided by 2. So now we can go back to our equation in black and we can change sine x cos x on the left-hand side to be a half sine 2x. So let's do that. Now our equation is a half sine 2x is equal to 1 over 2 root 2. We can probably multiply both sides by 2 to get rid of the halves. But before we do that, actually, we should make note that whenever we are solving an equation and the angle we're working with is 2x or 3x or some multiple of x, if you want to make sure you don't miss out on any solutions, and this is in my advanced playlist as well, you need to make sure you are applying the same multiplication to your domain. So by that I mean in the original question we were solving for x between minus pi and pi, but because the equation we're working with here in blue is now got a sine 2x, we've got to take our domain and we've got to double it. So x is between minus pi and pi. That means that 2x is between minus 2 pi and 2 pi. So we're going from negative 360 up to 0 up to 360. Okay, that's really important. If you forget that step, you are going to exclude some of your solutions and throw away some marks. So we're not going to forget about it. Okay, now that we've remembered that, now we'll multiply both sides by 2. So we get sine 2x is equal to 1 over root 2. Okay, let's think about some angles that go with sine and give us an answer of 1 over root 2 and give us a positive answer. So 1 over root 2 is the answer that you get for exactly doing sine of 45 degrees. So we're going to be doing 45 degrees in quadrants that are positive for sine, which is the first quadrant and the second quadrant. So 45 degrees in the first quadrant is 45 degrees, which is pi on 4. If we go into the second quadrant, we're going to do 180 take away 45, which is 135. And 135 degrees in radians is 3 pi on 4. So there's our two solutions going from 0 to 2 pi. What about the ones going towards the left, going from 0 to minus 360? How do you find those other two? Well, again, I really recommend you rely on your knowledge of what a sine curve function looks like. This is what it looks like. We can see here the blue line is on 1 over root 2, so it's the right-hand side, 1 over root 2. And we can see on the right-hand side, our two solutions we just figured out. The first one was 45 degrees, pi on 4, and the second one was 135 degrees, or 3 pi on 4. Okay? So, because we know what the shape of sine does, if we go to the left, it's just a repeating function, and then the quadrant between minus pi and minus 2 pi is the same shape as the quadrant from 0 to pi. So if we recognize this sort of reflective property, we can say, all right, cool. So if I want to find these two same points happening over here between minus 180 and minus 360, I've just got to go minus 360 and plus the 45 degrees. And I've got to go minus pi and then minus the 45 degrees. So I'm doing the same thing here. Here I plus 45 to get here, and I minus 45 to get here. I'm going to do the exact same thing, but it's going to be in this negative quadrant over here on the left. So minus 2 pi plus pi on 4, and minus pi on 4. That's going to get me the same shape happening over here. Hopefully that sort of makes sense. But that's how we do it over here. Minus 2 pi plus the 45, and minus pi minus the 45. Okay, this gets us our 4 answers for full marks, which are pi on 4, 3 pi on 4, minus 7 pi on 4, and minus 5 pi on 4. Those are the 4 values for 2x. So to finish it off, we're just going to cut them all in half because we don't want 2x, we want 1x. So dividing everything by 2, these fractions now all turn into over 8. And those are our 4 answers for this question in black up here. Sine x cos x equal to 1 over 2 root 2. Okay, so stepping up. Like I said, this is tough maths today. This is a really challenging part of the Extension 1 course. Some of my students have said that Extension 1 trigonometry is the hardest part of the course. I don't know if I agree with that, but I agree that it's definitely very challenging. So if you're getting a bit wigged out by these questions, just know that you're not alone, and it does take time to build confidence in solving these and using all your identities. It's a lot of content, so just go easy on yourself, okay? All right, on to example 4. We have tan 2 theta equal to negative tan theta, and we're solving for theta between 0 and 360, aka 2 pi. Okay, so where do we start? Well, first thing my brain looks at is it sees tan 2 theta, and it says, just like in the flashback, I know another way of writing tan 2 theta. I can write tan 2 theta like this, okay? And I can do that because I have memorized the identity for tan 2 theta. If you're not there yet, you've just got to go to your reference sheet like in the flashback. You've got to write your tan for sum formula. And then you've got to cough while you're explaining something. And then refuse to edit it. And then you're going to change the A and B to both be theta. And it's going to give you the same answers I've got over here in blue. But anyway, memorizing is the quick way to get there. Highly recommended by Mathematics. Okay, now where can we go from here? Well, I can see on the left and right hand side of the equation is a tan theta. So if tan theta was equal to 0, that would solve the equation straight away. So let's just say, well, if tan theta equals 0, that's going to work. It's not going to be the only solution, but it's going to be one of them. Now, where is tan theta equal to 0? Well, again, if we close our eyes and visualize what the tan graph looks like, which hopefully you've done at this stage in the course, you'll know that tan theta is equal to 0 at the same places where sine theta is equal to 0, because tan is sine over cos. So tan theta is equal to 0 at 0, pi, and 2 pi. It's the same places where the sine curve passes through the x-axis. Okay, now we've found those solutions. Now we can say, all right, going back to the equation in blue, what if tan theta wasn't equal to 0? Which means now I'm allowed to divide by tan theta because I'm not dividing by 0 because I've ignored those solutions now, okay? So whenever you're dividing by sine, cos, or tan from both sides, you are allowed to do it, but you have to do that after you've already considered the case where the sine, cos, or tan could be equal to 0. Otherwise, once again, you are going to be ignoring some solutions and you're going to be throwing away marks. But now we've done that work, we can divide both sides by tan theta, and now our equation's a little bit simpler. We have 2 over 1 minus tan squared equals negative 1. Let's just multiply the 1 minus tan squared across the right-hand side, so we don't have a fraction on the left, so it's going to look a little bit more simple, I suppose. So 2 on the left-hand side now, when I multiply the 1 minus tan squared over to the right with the negative 1, it's going to make the 1 into a negative 1, and it's going to make the negative tan squared into a positive tan squared. Okay, looking nicer already. Now I'm just going to add the minus 1 across the left to make tan squared theta equal to 3. Now we can just take the square root of both sides, but don't you forget to do that bloody plus minus or you'll be throwing away solutions and marks. Okay, so now to finish it off, we are solving tan theta equal to plus minus root 3 between 0 and 360. So root 3 is the magic number that you get when you do tan 60, which is pi on 3. And because we are plus minus, positive or negative, that means we are going to be occurring in every single quadrant. So we have 60 degrees in quadrant 1, 60 in quadrant 2, 60 in quadrant 3, which we get by doing 180 plus 60. And then we do 60 degrees in quadrant 4, which is 360 minus 60, okay? All right, so there's our answers in degrees. Let's just finish it off because the domain was given to us in radians, so our answers need to be in radians. So turning these into radians answers, we get a little bit of space, and then we get 0 from here. We get pi on 3 from the 60. The 120 is a 2 pi on 3. We get the pi from here. Don't forget our answers in red, so pi is there. 240 is the 4 pi on 3. 300 is the 5 pi on 3, and then 2 pi from our tan theta equal to 0. So we have 1, 2, 3, 4, 5, 6, 7 answers. Let's make them look real nice by writing them in order like I have here. And so we have 7 distinct solutions to this equation between 0 and 2 pi. So yeah, lots of overlap. The key point for this question here is the tan theta equal to 0 thing. You need to keep an eye out for this because yeah, it's really important. And also just knowing your identities and knowing when to apply them is a really good way of approaching these questions. Okay, let's kick on with example 5. I forget how many we're doing, but we're doing at least 5. Yeah, this one is pretty tough. This is from the 20,000. This is from the 2008 HSC, which is a bit of a relic now, probably about as old as most people watching this video. But anyway, we have show that for all values of theta, sine 3 theta is equal to 3 sine theta minus 4 sine cubed theta. And then we're going to use that in part B to solve this equation from 0 to 360. Okay, let's dive into part A and then see how part A is going to help us achieve part B. So for part A, we see sine 3 theta. And again, because I'm an extension 1 teacher and I've done this before, I know when I see a sine 3 theta, the best thing to do is to write the left-hand side using our sine of sum formula from the reference sheet once again, and writing sine 3 theta as sine 2 theta plus theta. So splitting the 3 theta up into a sum. So once it's a sum, you can use the identity from the reference sheet and get some trigonometry involved. So on the right hand side, we have sine 2 theta cos theta plus sine theta cos 2 theta. Okay, now we need to turn. If we look at the target of the right hand side, the goal that we're trying to work towards is an expression just involving sine theta and sine theta. There's no 2 thetas, there's no cos 2 thetas. The goal is to turn the right hand side into everything involving a sine or a cos of a single angle. So to do that, we need to know all of our different trigonometric identities. First one we're going to need is that sine 2 theta, as I mentioned before, is 2 sine theta cos theta. That's going to go there. That's going to have a cos theta next to it, which is multiplying. And now we have a sine theta on the end. And now for cos 2 theta, if you've studied these in extension 1, you know there's 3 different ways of writing cos 2 theta. You can write this as cos squared minus sine squared, or you can write this as 2 cos squared plus 1, or you can write it as 1 minus 2 sine squared. So the really tricky part with cos 2 theta is that there are 3 different identities, 3 different ways of writing this expression, and you've got to pick which one is most relevant for the question that you're answering. Because I can see that my answer is involving sines, I'm going to turn cos 2 theta into the identity version that only involves sines. Okay, so I don't want the other two, I want this one because I want to be working in sines. Okay, now let's expand some stuff out and see where to go from there. When I expand out the first part, I'm going to get 2 sine theta and then cos theta squared because there's 2 of them. On the end, I'm going to get sine theta times 1, and I'm going to get minus sine squared times sine, which is sine cubed, and it's got a 2 in front of it. That was a really bad way of explaining that, but I feel like you get what I'm going for. Okay, we're getting closer there. We have a sine cubed, and there is a sine cubed in the questions. This is probably a positive step forward. We have a sine, and we have a cos squared, which is really ruining things. So last little bit of content knowledge here is to know how we can turn cos squared into sine squared by using the fact that sine squared plus cos squared is equal to 1. This tells us that, that if we rearrange that Pythagorean identity from the advanced course, so once again, sine squared plus cos squared is equal to 1. That means cos squared is equal to 1 minus sine squared. This is good because now I can expand this out, and what do you know? Everything is just in terms of sine. There are no causes, there are no worries. So expanding it out, we get 2 sine theta times 1, and we get 2 sine theta times negative sine squared, which is going to get us 2 sine cubed with a negative theta. Okay, now we can start grouping some stuff together. We have a 2 sine theta and a plus sine theta. That's going to make a 3 sine theta. And we have a negative 2 sine cubed minus a 2 sine cubed. That's going to make us a negative 4 sine cubed. And suddenly we have worked towards the answer and we have finished it. So we write QED done. Left-hand side equals right-hand side. Okay, that was pretty hectic. There was a lot of identities in there, but hopefully that's going to make our life a little bit easier for part B. Let's have a look. Part B. Yes, part B. Okay, here we are. Part B is solve the equation. Sine 3 theta plus sine 2 theta is equal to sine theta. And the result we achieved in part A is that sine 3 theta is equal to this. So it's probably going to be a really good idea to take the sine 3 theta in part B and replace it with a 3 sine theta minus 4 sine cubed. So let's do that. Now we have a 3 sine theta, a minus 4 sine cubed, and a sine 2 theta equals sine theta. So where can we go from here? There's not really much we can put together. We can put the sine theta with the sine theta, but we still have a sine cubed and a sine 2 theta. So it's probably going to be really smart to turn all of our expressions into things involving sine of 1 theta. So once again, we are relying on our content knowledge and knowing that we can write sine 2 theta as 2 sine theta cos theta for like the third time today. So what I've done there is I've moved the minus 4 sine cubed to the front. I've taken sine theta off both sides, which has turned this 3 sine theta into a 2 sine theta. And I've, just rewritten the sine 2 theta as a 2 sine theta cos theta equal to 0. Now, why is this good? Well, because now everything's in terms of 1 theta, which is good. All our angles are in the same sort of, metric. And what's also good is that I have 3 terms on the left-hand side, and they all have a common factor. I can actually pull a 2 sine theta out of all 3 pieces. That's probably what I'm going to do next, if I can remember correctly. I did, yay. So when you pull out 2 sine theta out of the front term, we get negative 2 sine squared left. We get a cos theta left from the end, and the 2 sine theta turns into a 1. I've just written those in a different order, and you'll see why shortly. Now we're going to split this into 2 distinct equations. The first one is the 2 sine theta that's multiplying at the front. We can see what happens when that's equal to 0. And the other thing we're going to solve is the much more tricky quadratic in the middle. So the way we're going to handle this is that because we have a sine squared here and a cos here, we need these two to match so that we can solve this like a quadratic. Now the issue here is that it's really hard to turn cos theta into sine theta. What's a little bit easier is to turn a sine squared into a cos squared. So when these two don't match, the easiest one to change is the squared at the front, because we can once again use our rearranged Pythagorean identity, and we can say, cool, I'm going to write sine squared as 1 minus cos squared. While I'm here, I'm just going to divide the 2 off the front because it's not really doing anything anymore. It's just going to be a sine theta equal to 0 as our second equation. So inside we have minus 2 times 1 minus cos squared. We have a cos theta still, and we have a plus 1 still. Okay, if we expand out the inside and simplify a little bit, we're going to get minus 2 times 1, which is minus 2. Add the 1, and we get minus 1, which I'm going to put on the end. Minus 2 times minus cos squared theta gets us positive 2 cos squared theta. And the cos theta is still just chilling in the middle here, not doing much. So there we go. We have re-expressed the inside. So now it's a quadratic in terms of cos rather than a mismatched sine squared and cos. Okay, solving the first part, we can... Okay, that was a bit of a jump there. What I would normally encourage my students to do now is to, if you want, change these cos squareds and coses to be u's, so it looks a little bit more like a quadratic equation, and then either use some factorizing or using the quadratic formula. I'm trying to keep these as brief as possible, so I'm going to skip that step, and I'm just going to show you what this inside looks like when you factorize it using, whatever method you use to factorize quadratics. Factorizing this, it is going to turn into 2 cos theta minus 1 and cos theta plus 1 as your two factors, okay? But again, you can solve this inside part however you want. I'm just trying to be brief. Now we have 3 equations to solve. We have 3 things multiplying, giving us 0 for an answer. We have either sine theta is equal to 0, we have 2 cos theta minus 1 is equal to 0, or we have cos theta plus 1 is equal to 0. We're going to do all 3 of these independently, starting off with the sine theta equal to 0. Okay, so what's happened there is I've done sine theta equal to 0. In the middle, I've just moved the 1 across and divided by 2. So I've got cos theta equal to a half. That's our solution for the middle bracket. And for the end bracket, I've moved the plus 1 across to become a minus 1. So this is what our 3 equations are going to look like when we simplify them a little bit. Okay, now sine theta equal to 0. Once again, relying on our idea of what the sine graph looks like. This gives us an answer of 0, 180 and 360, or in radians, 0, pi and 2 pi. For the bit in the middle, we have cos theta equal to a half. Now this happens when theta is equal to 60 degrees, or pi on 3. And because we are looking at the entire first lap of the circle, this can be in the first quadrant for cos, or it can be in the fourth quadrant for cos. This could be 60 in quadrant 1, or it could be 300 in quadrant 4. That's going to give us 60 and 300 right there. And for the last part, cos theta equal to -1. Again, thinking about your cos graph and what it looks like, the bottom part of the cos graph is the -1, and that's occurring at the halfway point, which is at 180, which is pi, which we've already got, but I'm going to write it again because why not? So 0, pi, 2 pi from the first part. From the middle part, we get 60 and 300, aka pi on 3 and 5 pi on 3. And for the cos theta equal to -1, we just get pi, but it's already happened. So rewriting our questions, getting rid of those duplicates and just rewriting our answers, getting rid of the duplicates and arranging them in ascending order, we end up with 0, pi on 3, pi, 5 pi on 3, and 2 pi as our 5 answers for this one equation in the 2008 HSC. Man, I've been back at work for one day and I'm so tired and it is drastically affecting this video, so I apologize if you've made it this far and you're like, what is this guy doing? Okay, I think we got one more for this lesson. We got 2 more. I think I'm going to take a break. All right, I've taken a break. I've had a glass of water. I've toughened up. I'm ready to finish this off today. Okay, finishing off the examples before we do one more HSC one. This is a very, very rare type of question. I'll kind of put it in this lesson as a just in case memo, because Nessa has said they could assess these, but they haven't really been assessing them in recent years. But you never know what those sneaky dogs will do this year or in future years. So we have find all solutions for cos theta equal to √3 on 2. So normally when we're solving a trigonometric equation, we are given some sort of range for our values of theta, usually from 0 to 360 if they're being nice. This one they've just said, and by they I mean me, they've said find an expression for all the possible solutions for cos theta that give you an answer of √3 on 2. So let's start off by thinking about what this looks like. The first answer that gives us √3 on 2 when we're working with cos is when theta is equal to 30 degrees. Okay, that's in the first quadrant because we're positive. Because we're positive, it could also be happening in the fourth quadrant, which is 360 minus 30, which is 330. But the thing is, this is just the first 2 of an infinite series of solutions. We could get the next 2 by taking these answers and then just adding an extra 360 or adding a 2 pi to them. So any solutions that are on these 2 blue lines, on the 30 and on the 330, they are going to be valid solutions. It could be, the next one is going to be 30 plus 360, doing another lap. The next one after that is 330 plus 360, doing the next lap, and so on and so forth. So we need to try and find a sort of clever or intelligent way of writing all our solutions being either from 30 or from 330, and then either going forwards or backwards by some multiple of 360. Because remember, we could also go to the left and look at -30, look at -330, and so on and so forth. So the way we're going to do that is we're going to say, all right, we could be doing from the start, we could be going off this line. If we could get that picture back. From this line, we're always going to be going either 30 degrees up or 30 degrees down. That's going to be 0 at the start, plus 30 minus 30. If we do a lap, that's going to be 360, and then plus 30 minus 30. Then the next lap, and so on and so forth. And that's where I get this expression from. 0 plus or minus 30. The next lap, 360 plus or minus 30, and so on and so forth. Okay, so a clever way of writing this would be, we want to do any multiple of 360 and then add or subtract 30 degrees from it. So it's going to look like this picture. So for questions like this, where you're trying to find all solutions, really recommend you draw yourself a little picture like I've done, and then try and find a clever way of writing, like I've done here, a clever way of writing all the series of solutions. So we could have 0 plus or minus, turning it into radians now, because we're in year 12 and we do real maths. 0 plus or minus pi on 6, 2 pi plus or minus pi on 6, and so on and so forth. So the clever way of writing this is we're going to be doing all the multiples of 2 pi, but then we're going to be plussing or minusing pi on 6. So we can write that as 2 pi times n plus pi on 6, where n is a whole number. It's going to give us this one when n is 0. It's going to give us this one when n is 1, this one when n is 2, and so on and so forth. It's always also going to give us the negatives, like -2 pi, -4 pi, because an integer can be positive or negative. So that last line there in blue is the most succinct way of writing all the solutions. But again, these are pretty weird. Thankfully, like I said, very rarely assessed. So hopefully it's not going to be a problem in your life this year, but maybe next year for my life, it'll be a problem. Okay, now we're finishing off with the last one. This is an HSC question from a recent exam. This is 2021 HSC, and it was a band 4 level question. 3 marks. We have a polynomial involving a lot of signs. And the question gives us a massive hint by saying by factorizing, or otherwise, solve between 0 and 2 pi. Okay, if you feel like you had your head around most of the examples in this video, I strongly encourage you to pause this one and give it a crack yourself. But again, if you're just here to observe and come along for the ride, let's dive into it. Let's start off by doing a bit of factorizing. So normally polynomials are pretty hectic to deal with, but because they said I can factorize this, would you believe I'm going to try and factorize it? I'm going to try and factorize it by grouping it into pairs because I'm looking at the front half and I'm like, boy, gee whiz, there's a couple of sine squareds and a 2 that I can yank out of these. Maybe that'll get me somewhere cool. So let's do that. Factoring 2 sine squared x out of the front 2 components of the polynomial leaves me with a sine x here and leaves me with a plus 1 here. Now that's really cool because on the end, I've got a sine x and a 1. If I take the negative out of them and factor that out the front, now what do you know? I've got another sine x plus 1. So now I've sort of manipulated the question so that now I have 2 expressions where there's a common factor of sine x plus 1 and I can factor that out the front. That's going to leave me with 2 sine squared x minus 1 for our other factor. And there we go, we have factorized and now life is easy. Now we can split this into 2 little sub-equations. We can solve sine x plus 1 equal to 0, and we can solve 2 sine squared x minus 1 equal to 0 individually. So starting off with the sine x plus 1, we're just going to yoink the plus 1 over to the right to become negative 1. And now we are going to think once again, close our eyes, visualize what does sine x look like? Because anytime you're trying to solve equal to 0, 1, or negative 1, you've got to think about the graph. So thinking about my sine graph, it starts at 0, it goes up to 1, and then it goes down to negative 1 when it's 3/4 of the way through. Okay, so this happens when x is equal to 3 pi. Oh no, sorry, it's going to be 180 plus 90, which is 270, which is 3 pi on 2. I feel like I was about to say that, but then I didn't. Okay, so again, solving this just by looking at our sine graph and doing a bit of graphical calculations, we get x equal to 270 degrees, which is 3 pi on 2. Now for the slightly more spicy section, we have the 2 sine squared minus 1 equal to 0. We are going to add the 1 across and then divide by the 2. So we get sine squared equal to 1 over 2. We can then take the square root of both sides, but don't you please forget to do the plus minus because you're going to be throwing away solutions and marks, which is kind of like the thing we're trying to avoid doing today. Now thinking about where is sine x equal to 1 over root 2. 1 over root 2 is the fraction that we get from the magic number of 45 degrees, aka pi on 4. And because we are plus minusing once again, it's going to be in every quadrant. So we're going to have 45 in quadrant 1, 45 in quadrant 2, quadrant 3, and quadrant 4. So to get our full 3 marks, we've got to have all 5 of these answers together in 2021 for our band 4. But again, this one was nice because it was factorizable and it was just between 0 and 2 pi. There was no extra loops or no negative domains, anything like that. This is pretty friendly, but again, it's still a band 4, it's still tough. Okay, that will do it for today. If you made it to the end of that, congratulations, because you're much braver than I, because I had to go get a little drink of water. But if that wasn't enough punishment for you and you want some more extension 1 trig equations, come back in a couple of weeks where I'll be doing the rest of this topic and yeah, settling in for some more pain because I love trigonometry and I love this channel. And if you made it to the end and you're watching these videos, I guess I love you too. All right, goodbye for now, not forever. See you soon.